Okay, so what I want to talk about today is um, creating a decision tree and then building up to a random forest, just so you get an idea of how uh, this kind of model works. And I'll show you how to kind of build a random forest in using tidy models. And actually, your third homework assignment is going to kind of just walk you through that process of making some predictions with tidy models. And so that will get you started as far as creating a submission. And so as part of your third homework assignment, you have to make a submission to the Kaggle project as well. Okay, so a decision tree basically takes your data set and it starts partitioning it into smaller chunks. Okay, so it uses variables from the observations to kind of split the data into smaller chunks, and at each split it takes one explanatory variable, okay, and it forms a binary split using a simple rule. So if you have a numeric variable, okay, so for example, let's say we are trying to predict, these orders, okay, order total here. So we look at this thing, we look at our response variable, okay, and we're trying to predict our response variable, and we're going to form some kind of binary split, okay? And so maybe we'll take a numeric variable like count, and we'll split it between rows where the count is over 100 and rows where the count is under 100. Okay, so maybe that will be one possible split. Okay, so if the explanatory variable is numeric, the split will be of the form, pick some threshold, and you'll have the rows where x is less than 100 and the rows where x is 100 or greater. Okay. If you have a categorical variable, for example, say state, okay? So state is categorical, there's 50 of them, okay? And basically you'll have some kind of, you'll split the 50 different states and you'll make two piles. And you'll say, okay, over here we're gonna put, I don't know, California, New York, Texas, Florida, these big population states, okay? And then we'll put everybody else in the other category. So maybe you'll have like the 5 most populous states. I think California, New York, Texas, Florida, and I want to say Ohio, or is it Pennsylvania? I don't know. Okay, so you take these states with high population, you put them on one side. You take all the other 45 states or something, you put them on the other side. Okay, so you just split them in the form of, the row belongs to, one group, or the row belongs to the other group. And then so once you do that, now you have you've taken your entire data set and you made 2 smaller groups, okay? And then you just take one of the smaller data sets and you split it again, okay? And so you just continue to partition. And so this is also known as recursive partitioning, but we're forming some kind of tree. So this binary partitioning continues until you reach some kind of stopping criterion. And then after you've made all of these partitions, all of the observations that fall in a certain bucket, you make just one prediction. You basically just take the average of everybody in there and you just make a prediction, okay? And that's how you do a tree. So you can, I guess your final prediction could either be numeric or categorical. If it's a numeric prediction, we call it a regression tree. If it's a categorical prediction, it's a classification tree. Okay, so we'll start by looking at regression trees. Again, regression trees are used to predict a numeric response variable. And the way it's going to work is it considers every single possible partition. okay? So it looks at your kind of partition options, and it considers every single possible partition. And then what it will do is it's going to choose the split that minimizes the residual sum of squares after making that partition or split. Okay, we call this a greedy decision. We say the algorithm is greedy, but maybe a better way is just like immediate. It's kind of like seeking the immediate satisfaction right there. Okay. This is an old decision tree that was published in the New York Times back in, I think, 2008. So I guess, 17 years ago or something. The thing about decision trees is that they're very easy to read and understand, okay? So if you have a single decision tree, it's very easy to kind of read it and understand exactly what's going on. And so this was... they used a decision tree to try to predict whether. So this was during the prior to the 2008 presidential election. There was the 2008 presidential primary. Okay, and so there were different Democrat candidates running to be the Democratic nominee. There were candidates running to be the Republican nominee in 2008, and at the time, the leading candidates for the Democratic nominee were Obama and Clinton. Okay, Hillary Clinton and Barack Obama, they were trying to become the Democratic nominee for president. And what this decision tree was trying to do is trying to predict which counties would vote for which Democratic nominee. So the way the primaries work in the United States is that different states vote at different times. And so this was kind of like halfway through the process. So several states had already voted, and then several states still hadn't voted. And so looking at the data from the states that already had voted, they looked at county level information. They said, okay, if we look at different kind of demographic traits of this county, who did they vote for? Okay, and actually, this is going to be kind of a similar project that you'll do for your classification thing. Okay, anyway, if you looked at the racial demographics of the county, okay, if that county had a population that was 20% Black or more, okay, then the decision tree says Obama wins these counties. Okay, so apparently there might have been 453 of these counties, and Obama wins these 383 to 70. Okay, and if the county did not have more than 20% Black, then you have another partition, and you ask another question. Is like, is the high school graduation rate higher than 78%? Okay. And then the answer is yes or no, and you have these different kind of things. So politics were quite a bit different in 2008, and so this almost feels very quaint if you read through this decision tree and who voted for what not. Anyway, in 2008, Obama ended up becoming the nominee for president, and then ended up winning the presidency in 2008. All right, but what we'll do is we'll try creating a decision tree ourselves, and we're going to use just a very, very, very simple toy data set, okay? And so here I have just one predictor, X, and X has the values 1, 2, 3, 4, 5, and we have one outcome variable, Y, and the outcome values are 1, 1, 3, 7, and 8, okay? And what we want to do is we want to consider every possible partition on X, and we will see what effect it has on the outcome variable Y, and we will see how we're going to pick the decision tree split criteria. Okay, so we form a baseline by saying, okay, where what is our kind of our baseline amount of error, our RSS, if we have no partition? This is kind of like in in ANOVA, you have your total variance, okay? And in ANOVA, you split your total variance into like between group variation and within group variation, right? And here we just kind of start off with the total variance or the RSS. And this is going to be, well, what if you just predict the mean for all of the values, okay? So our response variable is y, and our values are 1, 1, 3, 7, and 8. And if you add that up, you get a total of 20, right? And so the mean of y is 4. And so if you have no partition, your predicted value for everybody is going to just be 4. And then this over here is going to be your residuals. I left off, I guess I'm just doing absolute values here. Okay, so you take the difference between the actual and the predicted. You have a residual of 3, 3, 1, 3, and 4. And then over here you have your squared residuals. Okay, so you have 3 squared is 9. And so you have squared residuals of 9, 9, 1, 9, and 16. And if you sum all of these up, the total RSS is 44. Okay, so this is what we have. And so so that's going to be our baseline. And any split we do, we should see a reduction in our RSS. So this is kind of what our baseline picture looks like. We have y plotted at 1, 1, 3, 7, and 8. And here I'm just predicting 4. This is just the mean of all the values, and the dotted red lines are our residuals, and if we square them, we would get a sum of 44. Okay, so we're going to consider all possible partitions. And so looking at x, we have 5 unique values, so we have 4 possible partitions. Okay, I could put the first observation, x, I can draw basically a split at 1.5 on x. And I'll say anything where x is less than 1.5 will go to the left, anything greater than 1.5 will go to the right. And so I have partition A, and then I have partition B. And then so for the observations in partition A, there's only one observation. The value I would predict would be the mean of those observations. So there's only one y, it's 1. So I would predict 1. And therefore, my residual is 0, and my squared residual is 0. Okay. For all the observations in partition B, my y values are 1, 3, 7, and 8, which add up to 19. 19 divided by 4 is 4.75. So I would predict 4.75 for all of these observations. These are my residuals, and then if I square them, I get this. And if I add up all of these squared residuals in total, I would get 32.75. Okay, so we do see a reduction in RSS. We go from 44 down to 32.75. And this is what our picture looks like. Okay, so here I'm getting this one exactly right, so I have no residual here. And here I have some error, okay? In the dotted red lines, I square them up. If you sum them up, you get 32.75. Okay, so continuing on, we can say, all right, well, what if we split between x greater than 2.5 and those less than 2.5? Okay, so in partition A, I'll have these first 2 observations. For these first 2 observations, y is 1, and so my predicted value will be 1. Okay, so I'm going to have 0 residual. For the other partition, the values I have 3, 7, and 8. The average of those is 6. Okay, and so my residuals will be 3, 1, and 2, and my squared residuals will be 9, 1, and 4. Okay, and so if I add up all of my squared residuals, 0 plus 0 plus 9 plus 1 plus 4, I get a total RSS of 14. And this is what my picture looks like. And so you can see we have no residuals over here. We're getting these ones predicted perfectly. These ones we have some error. The sum of the squares for these residuals is 14. Okay, going on, I'm going to split between 3 and 4. Okay, and my average of 1, 1, and 3 is going to be 1.667. The average of 7 and 8 is 7.5. These are my residuals, and my squared residuals look like this. Over here, my residuals are 0.5 each, and my squared residuals are 0.25. And if I sum all of this up, the total RSS is 3.1667, okay? And so here are, and you can see this does a kind of a much better job, right? So we're predicting 7.5, so we're off only by basically 0.5 and 0.5, okay? And then over here we're predicting 1.67, so we have small residuals, and when you square all of these up, the sum of the squares is 3.167. Okay. And then lastly, we have one more split to consider. I will split between 4 and 5, and so if we put these 4 observations together, their values are 1, 1, 3, and 7, and so that adds up to 12. And the mean would be 3. And so we can calculate the residuals here. We get residuals of 2, 2, 0, and 4. And I square those, I get 4, 4, 0, and 16. On the other hand, I only have one observation, so I'm going to predict it perfectly. I have no residual and 0 squared. And so when you add all of these up, the RSS of this split is going to be 24. And this is kind of what the diagram looks like. So here, when you put these 4 observations together, the average value is going to be 3, but now you have a residual of basically 2 here and a residual of 4. And so when you square those up, you get something bigger. You get no residual over here. You get that perfect. Okay, so looking at the different possible splits. So here we have this split with an RSS of 24. We have this split with an RSS of like 3.167. Okay, here we have this split with an RSS, I think, of 14. And we have this split where we have an RSS of like 32.75. So between these splits, we're going to say this one does the best because the resulting RSS after making this split is the smallest of the different options presented. This one's RSS is only 3.1667. So that's the best performing split. And so we are going to split between x equal to 3 and x equal to 4. And that's going to be our partition, okay? So that's how we go about doing, choosing that, okay? We can replicate this in R. In R, there's different packages. And so here I'm going to use the package rpart. There's another package called tree, and this can be used to kind of create decision trees, tree and rpart. This is just using the package directly. Later on, I'll show you how to do it in tidy models, okay? So if you use the package directly, you're going to call library rpart, and then you put in the formula. Basically, in our case, it's going to be y tilde x. So much like you create a formula in LM, okay? And then you show the data frame where you can find the data, and then any other kind of control is going to be options regarding how the partitioning should be done, okay? The default settings in making decision trees is that it needs to have a minimum of 20 observations before it considers splitting it into something even smaller. Now, we only have 5 observations in our toy data set. So in our control options, we're going to say, you know, even if you only have 5 observations, please consider making a split. So this is what it's going to look like. I create my data where x is 1, 2, 3, 4, 5, and y is 1, 1, 3, 7, and 8. And then I'm going to create a tree by calling rpart y tilde x. Data comes from our data frame. And then I'm going to, in rpart control, I'm going to say, consider making a split even though we only have 5 observations. So let me go ahead and run that. Okay. All right, and so when you run that, this is the output of the tree, okay? It says n equal to 5, node, split, n deviance, y val, and then star denotes a terminal node, okay? So this is the output. And so this this output here shows that where we want to make a split is at x less than 3.5 versus x greater than or equal to 3.5. Okay, so this split right here reflects exactly what we decided right here. Okay, so we draw a partition between x is 3 and 4, right? And we can see our RSS is going to be 3.1667. When we split between 3 and 4, our predicted values are 1.667 on the left-hand side for partition A, and on the right-hand side for partition B, our predicted value is 7.5. And that's reflected right here as well, okay? So you can see our node, this node, the split happens at x less than 3.5. The n is 3. We have 3 observations where x is less than 3.5, okay? The predicted value when x is less than 3.5 is 1.667, that y value right here, okay? And then the deviance is basically the sum of your RSS for that particular node, 2.667, okay? When x is greater than 3.5, we have 2 observations. The predicted value for those 2 observations is going to be 7.5, and then the deviance there is going to be 0.5. So I want to show that it is exactly the same here. So here is our split. We split between 3 and 4, and our predicted values are 1.667 and 7.5, which match exactly the output of our tree right here, 1.667 and 7.5. And then the deviance is basically this RSS value, but just summed up for those observations. So when you can see for the 2 observations that where x is greater than 3.5, okay, it's going to be 0.25 plus 0.25, that indeed adds up to 0.5, okay? And then for these 3 observations, 0.44, 0.44, and 1.77, those would add up to 2.667. And when you add these 2 up, you get the total RSS of 3.1667. So that, so the results of running our part on our computer match exactly the results that we got if we did it by hand, okay? And so this just describes all of that, everything that I explained, and that matches our optimal split. The another thing that you can do if you have R part is you can call summary on the resulting tree, and this is going to be the output here, okay? And so there's a few different pieces, okay? So you have this term up here, CP for complexity parameter, okay? And so here it's going to say node number 1, we had 5 observations, okay? So this is kind of the top level node, and if we do make a split, its complexity parameter gets a score of 0.928, okay? Prior to the split, okay, the mean is 4, and it says the MSE is 8.8. So this is kind of on the in our initial, when we had no partition, okay, when we had no partition, we had all 5 observations there, and the predicted value would be 4. The RSS in total is 44, and if you do 44 divided by 5, you would get the mean squared error, okay? The mean squared error. So the sum of squared errors was 44, and the mean squared error would be 8.8, okay? And then, and you can do a split there, and on the left-hand side, you have 3 observations, and on the right-hand side, you'd have 2 observations, okay? And it's a primary split, would be x less than 3.5 to the left, and then the improvement is going to be an improvement of 0.928. That's the complexity parameter, okay? Here it says left sun equals 2. This indicates that once you make this split, now you're going to have a node. Node number 2 has 3 observations, okay? The right sun, that node number is 3, and it contains 2 observations. And here it says, okay, what's the mean squared error on the left and the mean squared error on the right, and so on and so forth. So this is just kind of additional information regarding the tree. The way this complexity parameter is found, okay, the way we calculate that is we say, okay, prior to the split, prior to making the split, our MSE was 44, okay? After we make the split, our MSE is reduced down to 3.1667. So how much did our MSE improve, right? So I can do 44 minus 3.1667, okay? So our MSE was reduced by 40.833, okay? What percentage is that of the total MSE? So I'm going to take this number, 40.833, and divide by 44. And it says, oh, you've reduced it by basically 92.8%. Okay, and that's what this complexity parameter is. How much of a reduction in RSS are you going to get by including this partition? Okay, so so it gives you that kind of information there. So and that's detailed out on this page. Okay, we can also create trees and whatnot using tidy models. Okay, so that's if you use RPart directly. And so in tidy models, you can make a decision tree, right? And so you say, I want to start off with a decision tree model. And you have different kind of arguments. And so here we're going to say the engine, as far as calculating a decision tree, is going to come from RPart, basically the RPart package. We're going to do a regression tree. And then we're going to fit it to our data by doing tree, and we pipe it into fit. Y predicted by X, data is equal to DF. And so this is going to create our fitted tree. All right, and you have different options. So let me go to Parsnip and tidy models, Parsnip, and we want to do a decision tree. Okay, and so these are some of the different things that can create decision trees. We have RPart, and then there's other ones, PartyKit and whatnot. Probably, however, decision trees by themselves less popular than, say, the random forest. Okay, so random forest, I would say, is the more popular choice for making decision trees. But anyway, if you want to do it, you can do this. You fit it. And then you can say, okay, what is the resulting fitted object? And we get the exact same result that we had when we called RPart. And it says it's a Parsnip model object, and then you can do that. Okay. The idea that we just saw here just generalizes to anything that's bigger. So if you have a bigger data set with, say, 100 observations, then when you make a decision tree, it's going to consider all possible partitions. So you probably have 99 of them, okay? So you split your data on these. You consider all of those partitions, and then you pick the partition that maximizes your reduction in RSS, okay, or minimizes the resulting RSS. If you have multiple variables, then you're going to consider splitting, you'll sort on the first X variable, and then you'll consider 99 splits. And then you'll sort on the second X variable, and you'll consider 99 splits, and so on and so forth. And you'll consider, there's a whole bunch of splits to consider. So with 5 variables and 100 observations, you would have like 495 partitions to consider. If you have 1 million observations, now you have close to 1 million possible partitions to consider. And if you have a whole bunch of variables, then even more partitions. And so, regression trees, their performance can become slow with really big data sets. Thankfully we have some packages that kind of does some fast searching of these partitions, like Ranger and whatnot. They work faster than, say, some of the older packages like Random Forest and things like that. Okay, but anyway, this is that's how a regression tree would work. Okay, and so after you split your data, you would kind of repeat that process, looking at the resulting nodes, and you'd consider all the possible partitions across all the predictor variables, and you would continue to grow the tree in this kind of recursive manner until you reach some kind of stopping criterion. So you might say, all right, stop when the terminal node has fewer than like 20 observations or less, then stop. Or go until you reach a tree depth of 5. Okay, you don't want to go more than five levels deep or something like that. Okay, and then when you reach that terminal node, you just average all of the observations in that thing, and that's going to be your one prediction for everybody in that terminal node. Or if it's classification, it's just majority vote. Okay, it's just majority vote. And so, a lot of times in politics, we like to use demographic variables to partition people, and it'll be something like, are you, over the age of 50? Okay, if you're over the age of 50, you go to this side. If you're under the age of 50, this, and then they'll, are you, what's your race or ethnicity? And they'll put like, white versus non-white, or some kind of split there. Gender, and perhaps education level and things like that. And then so you might say, okay, just imagine, okay. Over 50, male, white, non-college educated, predict how this person might vote, okay? You have person under 50, I don't know, however you want to go, and you can say, well, okay, well, now predict how the person might vote or something. And obviously, not every single person that falls into that bucket is going to vote exactly the same way, but it might, as you kind of split, so the general population might be close to a 50-50 split or something, but if you partition it down into these different buckets, you might get a bucket that's closer to an 80-20 split, okay? And then it's easier to kind of predict that way. And so you're not going to get everybody right, but it might be, a little bit more, you can classify things in each of these buckets at the end a little bit better. Okay, if you kind of follow this process of recursively creating more and more splits, and you end up with a tree, you can end up having a tree with kind of too many terminal nodes that ends up overfitting the data. And then so we might say, okay, wait, let's get rid of some of these splits. Let's get rid of some of these, I guess, like branches in the tree. And to kind of, I guess, stick with the tree analogy, we'll say this is called pruning the tree, okay? And so one example of a tree that's overfit, I'm going to say, hey, continue making splits. Even if you only have 2 observations, consider making a split, okay? And then consider splits even if the improvement in RSS is less than 1%, okay? Or is like only, as long as it's over 1%, consider that, okay? And so if we do that, I will get a tree that is overfits our data, okay? So here, I end up having a tree with 4 terminal nodes, okay? And basically I have 4 unique values of y, right? My y values are 1, 1, 3, 7, and 8. So I just have 4 unique values of y. And when I overfit my tree, basically I have put each unique value of y in its own terminal node. So I said, okay, first look at if x is greater than or less than 3.5. If it's less than 3.5, it goes over here. And then for the observations, I have 3 observations there, and then consider a split between basically at 2.5. And so if x is less than 2.5, then that, x is basically 1 or 2. Our predicted value is 1, and we have no deviance, okay? And if x is greater than 2.5, then x is 3, right? Because it has to be less than 3.5, but greater than 2.5, and I just have 1 observation, and my predicted value for y is 3, okay? And then, I can predict 7, I can predict 8, and I have no deviance in any of these things. I've basically fit my output data perfectly, but we recognize I've probably overfit my data, okay? So this is a tree that overfits our data, and we're going to want to get rid of some of these branches, or we're going to want to prune the tree. So which one should we prune? The way which we prune a tree is we get rid of what we would consider the weakest link or the weakest branch there. So the split that basically improves our RSS the minimum, okay? And so that would be the split right here, because prior to the split, our deviance was 0.5, and then after the split, it dropped down to 0. But I'm only getting an improvement of 0.5, okay? Over here, my deviance prior to the split is 2.66. After the split, it's 0, but at least I'm improving my deviance by a little bit more of 2.66, okay? So you kind of look at each of these things and you say, well, how much did our RSS improve with each split? So, we started off at 44. Our first split brings it down to 2.6 and 0.5, so 3.167, okay? This split, the next split drops it down to 0, okay? And this split also drops it down to 0. But basically, prior to the split, we're at 0.5, okay? So for the split at 4.5, our improvement in RSS goes from 0.5 down to 0. We're getting an improvement of 0.5, okay? In total, what is that? Out of the total RSS of 44, I'm going to do 0.5 divided by 44. It's an improvement of only basically 1%, okay? Or 0.011. And so that would be what we call the complexity parameter of this node. How much improvement in RSS are we getting, okay? Meanwhile, the other RSS, we go from 2.66 down to 0. So our RSS improvement, it would be 2.66 divided by 44, and we get something around 6%, okay? So that these show up as our complexity parameter numbers. And so when you call summary on this bad tree fit, okay, the tree that's has overfit, we have complexity parameters for each kind of node. The first complexity parameter value is close to 93%. That other split is around 6%. The other split is just over 1%, okay? And then here, this last one is just kind of our minimum threshold. We said consider making any kind of split as long as the improvement is over 1%. Okay, and so we can see the complexity parameter of each of these kind of splits, and what is these nodes there. Okay, so what we can do is we can change the minimum complexity parameter value. So if we want to make sure we're not going to have a split of 0.011% improvement, we can say our complexity parameter, we need to have an improvement of at least 2%. Okay, and so this will create a split, a tree where we will keep the split between x less than 2.5 or x greater than 2.5, but we don't have the split at 4.5. Okay, so this split is preserved. Okay, we're still probably overfitting, but you can see how you can adjust where the trees get split here. So as you're defining your trees, you can put in these additional parameters of like how much improvement do you need to see. Okay, and then so here's just another example of the tree where we're going to say only consider a split if the improvement is at least 10% or something like that. Okay, and in that case, then we just get back our tree with just one kind of split. Okay, and we don't have the split at 2.5. So that's how you can kind of mess around or use tidy models to fit trees and try out different kind of complexity parameters as necessary. Okay, we'll do just kind of another example. This one I'll take the CARS data set. Okay, so we have this CARS data set, I guess 19 CARS from Consumer Reports, and I think this is so we're looking at different vehicles, and we're going to try to predict the price of the vehicle based on the mileage, I guess gas mileage of the vehicle, the type of the vehicle, and which country it was manufactured in. Okay, and we're going to just make a decision tree. And so, you know, we have 117 different models, and so the first split is going to be based on the type. And cars, I guess we're going to put compact cars, small cars, sporty cars, and vans together in one group. And then the other will have large and medium cars. And this is going to be kind of the resulting RSS. And so if a vehicle is compact, small, sporty, or a van, we would predict its price to be $13,000. Okay, and if it's a large or medium car, okay, then we predict its price to be $21,600. Okay, and then among those cars that are compact, small, sporty, or vans, we'll look at the country. Was it made in Japan, Brazil, France, USA, etc.? Or was it made in Germany or Sweden? And so if it's made in one of these countries, our predicted price is $11,555. If it was made in Germany or Sweden, our predicted price is $22,000. Okay. Similarly, if we look at the large and medium cars, we can look at the place. And so the large medium cars that were made in Germany and Sweden, $27,000 would be our prediction. For USA, Korea, and France, we predict $18,697, and so on and so forth. And you just kind of keep forming all of these splits. We can also kind of take a look at how much improvement we get with each node. And so we get complexity parameters values. And so we get, so that first split has a complexity parameter of 0.25. Other splits, we have improvements of around 14%, 8%, 6%, and then some of them improve, by only around 1%. Okay, we get some variable importance and things like that. Okay, anyway, these are just some of the summary information there. Okay. And so we might say, well, you know what? Let's try fitting, different trees, and maybe I don't want some of these splits, right? Because the improvement here, the complexity parameter is only around 1%. It's just barely over 1%. So maybe it's not worth keeping those splits, okay? And so what we can do is we can try to pick like a minimum complexity parameter for our tree using cross-validation. And we can say, okay, what if I build a tree and I'm going to keep all of the splits where the complexity parameter is only 1%, okay? And how well does this tree perform, okay? What if I build a tree but I use a different rule and I say, hey, only build a tree if the complexity parameter is at least 5%. So only keep a split if the improvement is at least 5%. Okay, so you're going to get a less complicated tree, right? You're not going to have as many splits, but we're going to say, okay, well, how well does this perform in cross-validation as well? Okay, so what we're going to do is we'll do tidy models, and we're going to set up a tuning grid, right? So we remember how to do this. We'll set up, we'll create v-fold cross-validation for us to use, and then we'll do a tuning grid, and we're going to try out different complexity parameters. And we'll say, hey, build a tree with this complexity parameter, and you get like an overfitted tree, and we say, how well does that perform? Try a tree with a different complexity parameter that doesn't fit the data as well, but we'll see how well it performs. And so we're going to just kind of try this, right? And then, so as far as trees go, there's different parameters that you can adjust, not just the cost complexity, but we're going to do that. Okay, so this is how we were going to do it. So we're going to define our tree model, and here, as we define how our model is going to be, we put our cost complexity as a tunable parameter, right? So let me just contrast this to an earlier slide when we wanted to fit a decision tree with our part in tidy models. The way we did that is we either left no arguments here, okay, or back here when we defined the decision tree, we put in things like keep a cost complexity of 2%, and that creates this kind of tree. Or here we said make a cost complexity of at least 10%, and that makes a simpler tree over here. Okay, so we're going to do the same kind of thing here, but we're going to make cost complexity a tunable parameter, our complexity parameter there. And then we're going to try out several different values. Okay, and so our cost complexity, I'm going to do a range from -2 to -0.5. This is log. It says log 10 transformation, and so basically, these are my different levels of cost complexity, and I'm going to try 1%. That's -2, and then I'm going to have 0.0147, 0.0215, 0.036, 0.04, 0.068. So I'm going to try all of these different cost complexity parameters, and we're going to fit a decision tree we're going to do v-fold cross-validation. So maybe I'll do 10-fold cross-validation. I'm going to fit the tree to 90% of the data, and I'm going to see how well that tree performs on the remaining 10%. And I'm going to follow the process. I'm going to say, okay, what if I fit a tree with a 1% cost complexity parameter to 90% of the data? How well does it predict the last 10%? Okay. What if I fit a tree with, a cost complexity parameter of 4.64% on 90% of the data? How well does it perform on the remaining 10%? So we're going to do that. I'm going to do v-fold cross-validation. I'm going to set up my workflow, right? I don't know, am I doing this too quickly, or is this feeling okay? Yes, question.
Yeah, why did you transform, do the log why did you specify that range?
I didn't have to, okay? I could have said go from 1% to, 30%. And if I didn't do a log transformation, then it would be linearly spaced. So it would be, I guess if I did, let's say 1% to 31%, it would, and I said 10, maybe it would be like 1%, 4%, 7%, 10, 13, 16, so on and so forth, right? It would be linearly spaced out. I thought it would make more sense. This is just kind of my opinion that for the smaller values, they should be more closer together. And then as we get to the bigger values, I can just take bigger steps. So I'll go from 10% to 15 to 20 to 30. Okay. And so for something like that, this is, it's equally spaced out on a log scale. So basically I'm multiplying everything by like 1.47. So I'm going from 1% to 1.47. So linear space out is you're just adding a constant. You'd be adding 3% plus 3% plus 3% plus 3%. For log, you're just multiplying a constant, like 1 times 1.5 times 1.5 times 1.5 times 1.5 or something like that. And so, I don't know. That's just what I decided to do here. But, you don't have to. So this is just kind of I don't know, I guess a choice based on my experience that stuff like this might work better. Someone else might have just said, hey, just do a random grid, okay? Don't even bother evenly spacing these out, okay? These are just evenly spaced out on a logarithmic scale. Okay, so we will do that. We create our folds, our folds on our consumer report database. We'll establish a workflow, okay? Our workflow is going to combine our model. This is our tunable tree model along with just the variable selection. And here, this is just going to be add formula. If I wanted to, I could have a formal recipe where I do even more stuff, but we won't bother with that. So let me go ahead and just run this. Tiny models, pruning the tree. Okay, so we don't need to do that. Okay, so I want to do complexity, v-fold cross-validation. Okay, so this is going to be my my workflow, and then I'm going to run that workflow onto the grid. Okay, this is going to basically fit the model using the tenfold cross-validation and using the different complexity parameter values from TreeGrid. And so the results here are gathered on this slide. And so the tree results we have the results from all of our tenfold cross-validation, and if I want to see kind of its RMSE performance, I'm going to collect the metrics, and I'm going to just look at the RMSE. And we can see, and here I'm going to arrange based on the RMSE value, and we're going to ask, okay, which one had the smallest RMSE and for what different complexity parameters, okay? And so the one with the lowest RMSE is our trees with around a cost complexity parameter of around 3 or 4%. Okay, and we can see when my cost complexity parameter gets too big, like 30%, I'm only going to consider a split. At 30%, we can see my tree performance is not good. Okay, we have a high RMSE, but as the so cost complexities of around 3 or 4% seem to do okay. Cost complexity of around 1 or 1.5% do okay, but not as well, right? So we're probably doing some overfitting, right? And then around 6%, it's and 10%, our performance is going down. So it seems like our best performing model has a cost complexity of around 3%. So that's what we would use. Okay. Now, one thing about cross-validation is it is subject to randomness. So if I do the exact same thing, I'm just going to do it on different randomness. Okay, so I said knowing that v-fold cross-validation results are subject to randomness, I'm going to just do the exact same thing again, but just with different folded data, right? So I'm going to just take the data and I'm going to just shuffle it up and form, these 10 different splits again. So I just run the exact same code. I just run it with a different seed. This time, my best performing model had a cost complexity of around 2%, okay, rather than 3 or 4%. So this is just kind of just the random result here. But at least it's kind of in line. So something around 3 or 4%, maybe as low as 2%, okay? We're still seeing cost complexity parameters of 30, 20, 15% as performing poorly. Okay, so I guess, so to kind of go back and say, like, why do we pick the log? We can see, small adjustments at this area, going from 2 to 3 to 4%, gives us a little bit more insight. If I had a whole bunch of these things, 15, 18, 21, 24% or something like that, I probably wouldn't get that much insight. So it's fine that these are much more spaced out. Okay, here's another random seed, just doing it again and again, same kind of results. 2, 3, 4% have the best performing models. The 30%, 20% doesn't seem to go. Okay, so here around 2% seems to perform the best. Okay, so that is how one decision tree works. And we have, we say, okay, well, one decision tree is fine. Can we improve the performance of a model? Okay, and so what we end up doing is we say, well, you know what? Let's build a bunch of decision trees and combine them together. Okay, so having one decision tree is very kind of simple. It's very useful for interpretability. It's very easy to kind of explain. You can have that diagram. You can put it in the New York Times, and people will understand the graphic. Okay, but the drawback of decision trees is that its predictive performance isn't going to be very good. Okay, just because you're limited to just making one prediction for every single observation in that terminal node. So, so we have a few techniques. Okay. One technique is called bagging. Okay, you can create bags of trees, and this we apply this concept of bootstrap to our data, and then but we probably don't use bagging all by itself. We use bagging as part of our process to create the random forest. Okay, but bagging is one of the steps that we incorporate in random forest. Okay. And so we apply bootstrap, which basically just says, hey, your training data, why don't you just resample your training data? So just take the existing data and then just produce a new sample based off of it. Okay, so we're going to just resample our data with replacement, and we're going to get like another set of data that looks similar to your original training data, but is not exactly the same because you did this kind of resampling with replacement. So it's kind of like, if you have a deck of cards, you have 52 cards, and someone says, I want you to create another deck of cards that is similar to the original deck of cards, but not exactly the same. And you go, well, that's such a weird request, but okay. How are you going to do that? What you're going to do is you're going to sample 52 cards with replacement from that original deck. And so what you're going to end up getting is you're going to get another 52 cards, but because it's with replacement, some of the cards are going to appear more than once, and some cards are not going to appear at all. And so you're going to get another deck that just feels a little bit weird. It's going to be similar to the original deck, but not exactly the same. Okay. And that's what we do. That's Bootstrap. Is we're gonna resample our original data with replacement, and we're gonna get another data set that looks and feels kind of like the original data, but not quite. So it'll have some duplicates, it'll have some missing values. But what this does is it introduces some randomness. Okay, so now I have a data set that's a little bit different. Okay, and then now that I have a data set that's a little bit different, I'm going to say, hey, let's fit a tree to this data set. Okay, and when I fit a tree to this data set, I'm going to get a slightly different tree. Not exactly the same, it's one that's a little bit different. Okay, and then I repeat this process again. I resample the data, I fit a tree. I resample the data, I fit a tree. And I'm going to get a whole bunch of trees that are just a little bit different from each other. Okay, and the hope is that by having a bunch of trees that are a little bit different, when I come to make a prediction at the end, I'll run my observation through all of my slightly different trees, and then I'm going to average all of their predictions at the end. And we're hoping that by kind of averaging a variety, we're going to get something closer to the truth. Okay, so just to kind of illustrate, I'm going to reuse my toy data, and you can see how we're going to get just slightly different data sets and slightly different trees. Okay, so my original data, I have x is 1, 2, 3, 4, 5, and my y values are 1, 1, 3, 7, and 8. Okay, here I just resample my data, and when I do this, I end up getting the observations 2, 3, 4, 4, and 5. Okay, when I resampled, observation 4 got selected twice. I never selected observation 1. Okay, so we're just reshuffling and resampling our data. Some observations show up more than once, some observations don't show up at all. Okay, but now I'm going to say, hey, fit a tree to this data. Fit a tree to this data. Where should you make the split? Okay, and when we fit a tree to this data, it says, hey, split at x is 3.5. So this tree ends up looking very similar to before. We were going to say, hey, make a split still at 3.5. Okay. However, what is the value you're going to predict? The value you predict is going to be a little bit different. Okay. If your x is less than 3.5, predict a value of 2. If your x is greater than 3.5, predict a value of 7.33. Okay. So your prediction's a little bit different from our original tree, because I think the original tree way back here, we said split at 3.5, but if your x is less than 3.5, predict 1.67, and if it's greater than 3.5, predict 7.5. Okay, so we're splitting at 3.5, but our predictions are a little bit different. Okay, here I resample my data again. I get x, I didn't select row 2, but I ended up selecting row 3 2 times. Okay, and I say, all right, go ahead and make a split again. And here my tree says, hey, split at 3.5 again. Okay, fine. All right. And if you have x less than 3.5, what do you predict? This time we predict 2.33. Okay. And if x is greater than 3.5, what do you predict? We're going to predict 7.5. Okay. So just a slightly different tree. Okay. And if I do this one more time, this time just kind of by random coincidence, I ended up selecting observation 1 3 times and observation 4 twice, and I never selected observations 2, 3, or 5. But that happens by randomness, okay, sometimes. And so here I say, okay, make a decision tree, and it says, okay, well, split at x is 2.5, and if x is less than 2.5, predict 1, and if x is greater than 2.5, predict 7. Okay, and that's going to minimize that, right? So that's what we have. So we have 3 trees that are similar but different. Okay, all right. So let's say we have I've got 3 bagged trees, and let's say I have a test case where x is equal to 4. Okay, with x equal to 4, this first tree says predict 7.33. This tree says predict 7.5. And this tree says predict 7. So your prediction is going to be the average of these values, and you would predict 7.278. And that's That's how bagging works. Okay, so you resample your data by Bootstrap, get slightly different versions of your data, slightly different versions of the trees. And now that it's time to make a prediction, you feed your observation through all of the trees and then you average them. Okay, so that's bagging. Okay, now again, we don't generally do bagging by itself. Okay, it technically is implemented in Parsnip. In Parsnip, you can do bagged trees. But the problem of just resampling your data, you end up getting trees that just end up looking too much alike. Okay, it's like all the trees end up looking a little bit too similar, and so if one tree has a problem, then most of your trees are going to have the same kind of problem. Okay, so what we want to do is we want to try to bring in a variety of trees. Okay, and this is going to be random forest. Okay, so in random forest, we do bagging as part of it. We resample our data with Bootstrap, and when we make the tree, we put in additional limitations, and we say, when you make the tree, you're only allowed to split on these particular variables. Okay, so it's kind of like playing a game, and then you force people to have like different, encumbrances or handicaps. Okay, and so this. When this tree is being built, it's not allowed to use the variable gender, okay? And then when this tree is being built, it's not allowed to use the variable age, or and things like that. And you just randomly select which variables the tree is allowed to use, and the variables that the trees aren't allowed to use, and stuff like that. So you do this thing, and then so what you end up getting is a variety of trees, right? So I say, hey, figure out the best tree you can make if you're not allowed to use the variable gender, okay? Meanwhile, you over here figure out the best tree you can make when you're not allowed to use the variable age, okay? And so what ends up happening is that each of these trees, they might individually not perform as well as a tree where they were able to use all of the variables all at the same time. But instead, you have a tree that kind of specializes in, picking up, some of the signals or the patterns that exist among, maybe lesser variables and things like that. Okay. Over here, I said, another silly analogy is like if you're going to try to put together people for some kind of mission, okay? So like you have a heist, like every heist movie, they say like, oh, okay, we need the tech guy, and we need the driver, and we need this and that, right? And you might even have somebody, who's blind on your heist team, okay? And then if that's the case in the movie, there's going to be a scene in the movie where like the lights go out and nobody can see anything, but thank goodness we have the blind guy who is able to kind of get us through this part of the story, right? And it's kind of like by forcing everybody to have these like different skills and things like that, the team as a whole is made stronger, right? And that's kind of the idea of a random forest, is that individually these the individual trees don't perform super great because you put limitations on each one of them. However, in combination, and you kind of like put them all together, the random forest ends up performing quite well, okay? Rather than having, if the heist team, you just had like one Captain America who's like great all by himself, but then you have like 10 copies of the same thing, they're going to all have the same strengths and all have the same weaknesses, and so that happens. So with random forest, you basically do a bootstrap resample of the training data, and then when fitting a tree, basically you choose a subset of the predictor variables in the data set, and the tree is only allowed to use that subset of predictor variables, and you fit a whole bunch of these trees. Okay, and so this is kind of this diagram's from Wikipedia, and it just says, once you have all of these trees, when it comes to make a prediction, you feed that test case through tree 1, through tree 2, through all of your different trees. Each one kind of makes its own prediction here. This is a classification case, but it could be regression. It predicts a value, it predicts a value, it predicts a value. And so for classification, you do majority voting. For regression, you just take all of those different predicted values and average them together. And that's how it would go. Okay, so we can do something with like a different data set in tidy models. All right, and so in tidy models, we're going to take a look at the air quality data set, and we're going to try to predict this value ozone. And I forget, so ozone, it's like a special molecule of oxygen. I think it's like 3 oxygen molecules together. And in the atmosphere, it's really important. We need like the ozone layer. But then like if you have ozone at ground level, it's like not good for humans. It's like the oxygen like reacts too much with stuff in your body or something. So it's actually not good to have ozone down at the ground level. It's important to have it up in the atmosphere, but not good at the ground level. So anyway, we measure ground level ozone, we measure other things, and maybe we want to try to predict ozone here, okay? So what we're going to do is we're going to try to fit a random forest, okay? And then so as far as random forest goes, there's different packages that you can use, and this package Ranger, I would say, is better than the kind of original random forest package in R is called Random Forest, and then later on a higher performing package called Ranger came out. It's playing off of the idea of like having a forest ranger. And so I recommend that. If you're going to do a random forest model, I would say Ranger. Okay, so we're going to just establish a random forest model, and then we're going to throw it into a workflow so that we can kind of fit it to, cross-validation and whatnot and stuff like that. And so this workflow, we're going to just say, okay, take the model, and then as far as the formula, what we want to do is we want to predict ozone based on the other predictor variables. So I just have ozone tilde dot. Okay. And then if I say, all right, let's go ahead and fit the model to our data. Okay. Then I run into an error. It says missing data in columns. Okay. So let me do this with air quality, and yeah, you can see in our air quality data set we do have some values of solar.r missing. Okay, and so the random forest doesn't know what to do. Okay, it says, hey, we're missing. Here it says error, missing data in our dependent variable. That's also true. Okay, and so what we want to do is we're going to build a recipe that's going to start filling in some of the missing values. Okay, so our recipe, we're going to say, hey, predict ozone based on all the other values, but you know what? When you're missing a value in solar.r, just fill it in. And we're going to say impute the mean. So impute is, and there's a whole bunch of impute functions, tidy models, recipes. So let's go to recipes. And as far as reference goes, we have a whole bunch of imputation functions, okay? And so you can impute the mean or the median, however you want. So I'm going to just say, hey, impute the mean. And if I run this here, I still get this error that says we're missing values in our dependent variable, okay? Okay. And so in our case, if we look at our data, the ozone column itself, okay, we have a missing value in the ozone. So it's like, well, how am I supposed to predict this, okay? All right, so in the case where we are missing values in the output variable, okay, in the dependent variable here, we'll just get rid of those rows, okay? So I'm gonna just expand my recipe, and I'm gonna say NA omit. So this will just get rid of any row that's missing a value in the ozone column here. So, so we'll do that. So we're gonna say, hey, make our recipe, impute the mean, get rid of any missing values in ozone, and then establish our workflow, add the recipe, add the model, and then let's fit it to our data. And hopefully this will work. Okay, so we didn't get any kind of errors back there, so that's a good sign. I can say, all right, what is my fitted things? So my preprocessor says impute the mean, omit values, and then the result of Ranger says, hey, I fit a random forest, 500 trees, we got 116 values in my sample size, and overall it's R squared value is 72%. That's what we have, okay? And we can say, all right, well, let's try making a prediction, okay? Now, as far as this goes, we just trained it on the entire data set, okay? I didn't do any kind of train test split. I didn't do cross-validation, okay? So this isn't the ideal way, but this is just like, okay, you want to fit a random forest model, this is how we go, okay? So I'm going to take our fitted model, and I'm going to say, hey, make predictions on the data set that you used for training, okay? And so I just want to kind of just see its own kind of performance here. And we're going to say, all right, what did you predict and what was the actual value? Okay. And so, so we have these things, again, our actual data set does have some missing values there, so don't worry about it. But we can calculate the root RMSE, root mean squared error, by telling, the true values are in this column ozone. Our predictions, our estimates are in the column called .predict, and this is our RMSE. Our RMSE is 8.249, and that's what we have there, 8.24, okay? All right, there's another method called boosting, and we're gonna run out of time a little bit. The way boosting works is you create a tiny tree to the residuals, okay? So you start off by kind of predicting the average, you get all of the residuals, and then you're gonna just fit one tree, okay, one tiny tree to the residuals, and it's gonna say, all right, if your value is greater than this, add this number or subtract this number or something like that, okay? But you apply a learning rate, okay? And the learning rate just says, make tiny, tiny, tiny adjustments, okay? So, sometimes, like, if you need to make a correction and you say, okay, we need to head to the right, you might be tempted to just, like, steer all the way to the right, and then your aircraft or whatever, your boat or something, is going to suddenly take a huge sharp turn, okay? What boosting will do is basically it limits you and says, like, when you need to make an adjustment, you're only allowed to, like, turn a tiny, tiny, tiny bit, like 1 degree to the right or 1 degree to the left. It's like all of your corrections have to be tiny, okay? And that's what the learning rate will do, is when you fit the tree, it's going to say, all right, adjust your predictions by adding 100 or subtracting 50. and then you say, okay, if you want me to add 100, I'm going to just add 1. If you want me to subtract 50, I'm going to just subtract 0.5. All right, and so that seems to like hardly make any kind of improvements. But what it does is it does make just a slight improvement. Okay, and then you fit another tree again, and it says, okay, you need to add 99.5, right? Or like you added 1, so now you need to add 99, or you need to subtract 48 or something, and you just make tiny little adjustments each time. And it turns out by making a bunch of tiny little adjustments, the predicted performance is much better. Okay, so boosting learns slowly. We typically fit a bunch of small trees in each round. Small means 1 node, 2 branches, and it just trains on the errors. Okay, learns to predict the mistakes of the previous iteration. So here we're going to look at our toy data set. Again, 1, 2, 3, 4, 5, 1, 1, 3, 7, and 8. We calculate our residuals, all right? And we say, all right, let's just start off with a baseline. We're predicting 4 for everything. What are our residuals? Our residuals are -3, -3, -1, 3, and 4. And then when you fit the tree, it says, okay, if you're going to start off by predicting 4, then to get better performance, if it's greater than 3.5, add 3.5 to 4. So that would take you to 7.5. And if it's less than 3.5, subtract 2.33, and that would take you down to 1.67. Okay. But what we're going to do is we're going to say, oh, you want me to add 3.5? I'm not going to do that. I'm going to add only a tiny amount. Right? You're saying go up 3.5. Here, my lambda, just to kind of illustrate, I'm going to pick a really big lambda of like 30%, but normally it's like 1%. Okay. So we're going to say, oh, you want me to add 3.5 to 4 to take me up to 7.5? I hear you, but I don't want to make as drastic of an adjustment. So I'm going to add 30% of 3.5. Okay. So we take 4, we add 30% of 3.5. So I'm basically adding 1.05. So now my new prediction is 5.05. Okay. And if it was less than 3.5, we said, okay, subtract 2.33. And we say, well, I'm not going to subtract 2.33. I'm going to just subtract 30% of that. And then so I subtract 1.7 or whatever, or 0.7. And I go down to 3.3. So now my predicted values are 5.05 and 3.33. These are my residuals. Okay. And we say, okay, well, where should you make your split? Okay. You make your split at 3.5 again. If it's greater than 3.5, add 2.45. If it's less than 3.5, subtract 1.63. And we say, again, I don't want to add that full number. I'm only going to add 30% or subtract 30% of that. And so now my predicted values are 2.81 and 5.785. This seems kind of silly. I calculate my residuals. These are my residuals now. And then we say, okay, try to fit a tree on these residuals. My residuals are -1.81 and 0.19, 1.25. Okay, and this tree says, okay, now make a split at 2.5. Not 3.5, but 2.5. And if it's less than 2.5, adjust your prediction down by 1.81. And if it's greater than 2.5, adjust your prediction up by 1.2. And again, we say, I only want to do 30% of that. Or in a regular boosting situation, I only want to do 1% of what you're suggesting. Okay, and as we do that, we get different values. We get 2.267, 3.172, and we would just kind of continue this process over and over and over again. And eventually, right now you don't see it, but eventually we'll be making good predictions. Okay, we're going to be making good predictions. Right now, I just did kind of 3 iterations. I can kind of just show you like. So this process, and you can, if you look at every single number on each of these slides, you can, like if I say, how did I get this number 6.147, you can trace it back, right? On the math, the arithmetic, the work for each calculation to get to this number 6.147 is shown on the slides. You can follow it. We can also ask the computer to follow this process of boosting, okay? And so we would load in library GBM, and I can say, hey, fit 3 trees, okay? The shrinkage thing is going to be 0.3, okay? And if we do that and I say, hey, make a prediction where x is equal to 4 using our 3 trees, it's going to output 6.147, which is exactly what we got here. Okay. If we want to do it in tidy models, we can do that. In tidy models, I don't know if I can do the exact same thing that I did here from GBM, but a popular package for doing boosted trees is XGBoost, and it's a high performing model there. And so here we can kind of do the same kind of thing. We can say we have the same recipe, impute the missing values of solar R, get rid of missing values for ozone. Now my workflow is take the recipe and add the boosted tree model, fit it to our data, okay? And it takes a little while, it runs, and then we can say, okay, make predictions. What do you predict? And if you look at the RMSE there, it's a lot lower, 3.26, okay? And so this is just kind of straight out of the box with tidy models. Again, we just say, hey, take it, fit it to what you have and see how it performs. Okay, that's it for today's lecture, covering decision trees, random forests, boosting, whatnot. Start taking a look at your Kaggle competition data set. Follow along in homework 3. That should get you at least started. My hope to get you started with making predictions so that you can start building up models and things like that. If you're not part of a team, I will just arbitrarily assign you to one and send out the contact information. Establish your teams on Kaggle, and good luck. All right, and we'll see you guys next week.